I'm pleased to welcome you today to this event. I am Milenia Puma from CRF, Fiat Research Center. And so today we have organized this event in the context of the project C4IIoT. So the project is coming to an end. In fact, this is the last month of the project. So today the objective is to present the outcomes of the project to all people who are interested in the field of cybersecurity applied in the automotive and supply chain in general. So after this opening session, we will have a presentation from one of the partners of the project, the University of Novi Sad, the Professor Sdn Controller, will present an introduction to the project and will give an overview of the architecture. Then I will present the pilot use cases, and then we will have a presentation from Giorgos Stamatis from ITML, who will explain how the C4IoT solution is utilized for securing the infrastructure and to prevent, detect, and mitigate threats. And then we will close at 11 o'clock. So thank you again for joining, and I leave the floor to Srdjan to present.
Okay, so my task today is to present, to give some introduction to the project and present architecture in short. So the project is almost at the end. The end of the project is on 31st of May. So we have a complete architecture and complete system in place. The C4IoT project is, maybe we should read the full name, Cybersecurity for the Industrial Internet of Things. So the domain is Industry 4.0, and within this domain we are focused on the cybersecurity challenges that arise in Industry 4.0 settings, and especially targeting IoT systems, so Internet of Things systems, or as it says here, IIoT. And as we'll see, the framework architecture is chosen to cover some representative use cases in the manufacturing industry. And our host CRF is actually a use case provider, and we'll present two use cases that we used for demonstration in automotive sector. Demonstrations are in automotive sector, but the framework itself is a general solution for Industry 4.0 applications. This is our consortium. So we have, as I said, a use case provider, CRF. It changed name to Stellantis, so that's Stellantis actually. We have universities, SMEs, and big companies like IBM, HP, and so on. Yes, I would like to go through the project statement shortly, because I believe that it is informative and can serve as a good introduction of how we cope with the problems arising in described settings. So we aim to create, build, develop, test a unified cybersecurity framework that is a complete solution, end-to-end solution, holistic and disruptive security enabling solution to minimize the attack surfaces in industrial IoT systems. To do that, the C4IoT bridges various kinds of technologies. So C4IoT bridges cyber assurance and protection, machine learning, deep learning, as a subset of machine learning, edge, cloud computing, blockchain technologies, big data technologies, and so on, to reach these goals that you can see here and that we defined. Of course, we will go into a bit more details on every one of these technologies a bit later. I would like to mention, before we dive into architecture, to shortly mention some innovations that we provide that are part of the C4IoT project. This is an excerpt from a paper, our joint paper that we prepared, that describes the architecture, but also numbers the innovations, lessons learned, and so on. So the system that we developed features several innovations, like modern encrypted means of communication using attribute-based encryption and blockchain for additional security on multiple levels of machine learning enabled anomaly detection models, machine learning and deep learning anomaly detection models that detect, well, attacks, faults, errors, outliers, and various anomalies in the system. And then the mitigation engine, when such a thing is has been detected, mitigation engine provides a response to these anomalies to mitigate the consequences in minimal time. Besides this, we implemented some differentially private methods. Those are privacy-aware machine learning methods that can be used when the data, both training data and inference data, contains sensitive information, maybe disclosing identities and so on. So it works by introducing a noise into this data, so that the noise masks the confidential data, but does not mask what we needed perhaps to train the model. So those features remain intact, but confidential data and private data is masked out in this way. And as we will see, we introduce both hardware level and software level security for protecting data sources and the system. In general, in this domain of hardware level security, within the project, we designed, built custom IoT edge devices. Those are microcontrollers, Arduino microcontrollers, but with custom components tailored to these use cases and to the goals of the project, and we deploy them in a real industrial environment. Okay, I mentioned use cases. There are two use cases actually within the automotive sector. So it's a demonstration within the automotive sector, but with two use cases. The first one is the inbound logistics or smart logistics or logistics 4.0, but we call it inbound logistics. Yeah, so we can imagine factories, and factories receive various parts from various sources, and those parts are being shipped in the containers from the origin point to the factory. And what we want to do here is to track and manage, to track what happens on the way, maybe when these containers have been loaded to trucks or ships, but also what happens in the warehouses when the containers have been stored in various warehouses. So this is outside, mostly outside the factory. And these containers, every container has this device that I mentioned, that we designed, microcontroller that we designed within this project, attached to every container. It has various kinds of sensors, GPS, and so it gathers some amounts of information of what goes on with the container, with that container, and uses narrowband IoT, so mobile network, to connect, to send the data to the system, to the C4IoT, to the rest of the C4IoT framework. So that's inbound logistics. And the other use case is a smart factory use case. This is what happens inside the factory, within the factory. So we can monitor various kinds of robots, and we monitored AGVs, automated guided vehicles. So there are vehicles at the plant floor that are operated automatically. We attached some edge node devices. In this case, they're Raspberry Pis that they have much more processing power than those microcontrollers in the previous use case, and they contain sensors, and they contain track the data and gather the data related to the activities of these AGVs. But in this case, they're connected to the rest of the system using internal network in the factory. So that can be Wi-Fi, for instance, or it can even be wired network. So this setting is a bit different than the previous one. But again, the data is being analyzed and being fed to the rest of the framework for analysis. Okay, so those are the use cases. And this is the main picture of the framework's architecture. We do not have enough time to go into every detail. You see that there are a lot of components and a lot of arrows pointing the data flows. But having in mind these two use cases that I just described, we can put them in this context and explain in a bit more detail how they work. So first we need to notice that three layers of the architecture. The first layer is the edge node layer. It's this one down here. So here we have edge node devices for both of these use cases. This is related to the, it says trucks and warehouses, that's logistics use case. And the other is smart factory use case. Here we have a bit different edge node devices. Then the middle layer is a field gateway layer or fog. So this is what happens within the network of the mobile operator or the factory itself. And this is the cloud layer. This is where the rest of the components live, and where we have the most processing power and the most resources in the cloud layer. There are also what we call levels. So these are layers. Edge, field, gateway, and cloud. There are also what we call levels of communication. But I believe that today I don't have time to go into that. So let's just try to explain in bird's view how this system works. In logistics use case, as I said, at the edge, we have devices. I think I have, yeah, I should have, yeah, the picture here. So these are the logistics use case edge node devices, the ones that we designed and built, developed, and produced within the project. We even produced these casings. You see these boards inside. The board is a small board, but the case should also fit the battery that's large. The idea is to have a large battery that has a capacity to run the device for at least 2 months. So below the device, actually, we would put a battery and then close it like this and attach it to a container. We can see that here. So these are the containers with some parts. I don't know which parts, but they have here attached these devices. So these devices contain, I mean, in this case, there's a battery, there's a power source. They're independent of the other power sources, and they have SIM card that they use to connect to mobile network using narrowband IoT, NB-IoT, to send the data. But even, yeah, so we are here. Even those devices, so that's novelty, have in their firmware have implemented lightweight anomaly detection, as it says here. So it's a small autoencoder with one hidden layer implemented in C without using any libraries, without using Python libraries where we could do it in a few lines of code. It's written in C, and it's a lot more than a few lines of code. Pre-trained models that do some lightweight anomaly detection, even here, even in these microcontroller devices. And in the smart factory use case, we have AGVs. So this is actually an AGV, automatically or automated guide vehicle. So it's a vehicle that goes around the shop floor, and we attached a Raspberry Pi. This is just a Raspberry Pi device. Attach Raspberry Pi devices to those AGVs. These devices have multiple sensors. They gather large quantities of data of what goes on with the vehicle. As in the previous case, some anomaly detection methods can be run here. Since we have more power, more processing power, the processor CPU is much more powerful. We have a lot more storage. So this is a more powerful computer. We can run some methods there, and they connect to the rest of the factory network using, well, Wi-Fi, and feed the data. We'll go back to this picture. Feed the data to the upper layer. And the upper layer in this logistic use case is the network of the mobile net operator. Mobile operator whose network we use to connect from edge devices using NB-IoT. So there are some servers that we can use to run additional anomaly detection, additional detection of problems, since they are much more powerful than what we have at the edge. And the similar thing happens in the smart factory use case, but in this case, field gateway servers are in the factory. Okay, so some anomaly detection happens down here, some happens here, and this Medici tool is a tool used for flexible anomaly detection in terms that it analyzes the detected anomalies and confidence scores, and decides if the data needs to be fed to the cloud, offloaded to the cloud, because in the cloud we have this, what we call here, behavioral analysis and cognitive security module, BACS. It actually goes through all the 3 layers, but since in the cloud we have the most resources, strongest CPUs and GPUs, then we can run various additional anomaly detection methods here. The most powerful anomaly detection methods here. And when the incident is detected, okay, in the logistics use case, we're outside the factory. So we're outside the factory network. What can be done is that we can send alarms to the, what we have here, to the some snap-in for humans, for natural intelligence to the system, and alarm them of what's happening. But in the smart factory use case, we are inside the factory. So we have a mitigation engine that we can use to react automatically to faults, to attacks within the factory. So there's some components here that receive the information about the anomaly, and this component karmas then decides how to reconfigure the network so that the consequences of this attack or anomaly are mitigated. So it's an interesting component implemented even in Prolog, and then it uses Sdn Controller to control which parts of the network will be cut off to mitigate the consequences. That's one part of the mitigation engine. The other part is actually what can be used in logistics use case, BINSEC, that can verify security of the firmware of the devices themselves. So if the attack, they can be attacked by tampering with their firmware, but then this component would detect there's something wrong with the firmware of the device, and that's additional protection even in this logistics use case. So this is some description of what's going on, and we don't have that enough time to describe everything. As you've seen, I skipped whole parts of this architecture, but I believe that I did describe enough details so you can follow the demonstration that will follow later. Yeah, so this is the edge node layer, a bit zoomed in. A zoomed in picture of what goes on in the edge node layer, but I believe we went through this in the previous slide. So let me check. Yes. I will go back to this slide. Okay, then I think that I will stop here with the description of the architecture, and so I think that my time has run out, and maybe take some questions. That's it from my side.
Thank you. So thanks again for joining us today. I am Ilenia Puma from the Fiat Research Center, and I will present the pilot use cases. So CRF in this project is, as already mentioned, the pilot partner. So we have the role of end user. In the project. Today I will explain what we have done for testing and demonstrating the C4IoT solution, and which is for us the added value that we got from the project. So I will start explaining who we are and why we decided to participate in this project. Then I will explain which are for us the main important results that we got from C4IoT. And then I will go through the business aspects again of the added value for us, and then I will explain the pilot execution and the impact analysis and KPIs. So first of all, who is the Fiat Research Center? We are a company of Stellantis. We were part of FCA, and so now we are in this new company, Stellantis, and we are a reference hub for innovation and research. In fact, we have a lot of contacts with universities and research centers. We have many projects, and in particular, we are in the group of Stellantis Production Way. That is an approach applied to all plants worldwide, involving the whole organization. From safety to environment, logistics, quality, and so on. Our aim is the continuous improvement of all the areas of production in order to optimize the quality of the final product and meet the customer expectations. So the target for this is to eliminate all forms of wastes and losses. And to do this, we also have the world-class manufacturing in our company with its pillars. Here you can see the ones that are impacted by this project in particular. So the aim for CRF is to ensure the compliance with the Stellantis strategic research agenda and the potential for rollout to other plants in order to exploit the C4IoT results after the project ends within the Stellantis company. We have expertise in both in cybersecurity and risk management. In particular, we are currently working also in other projects that are related to cybersecurity, like Sdn and Concordia, that are two active projects. In particular, Sdn focuses on the certification of supply chain service providers. And Concordia also focuses on the cybersecurity in both inbound and internal logistics. But in the past, we were also involved in other projects like Disrupt, Imagine, Boost, or MIDI that are projects that also focused, for example, disrupt on the assessment of impact and optimization of network, or for example, in MIDI, we already did some tests of devices applied to the inbound logistics. We have big expertise in these aspects, and moreover, we also have some internal projects, both with supply chain management and manufacturing in Stellantis companies. So why we participated to C4IoT in the company? As I said, we have lots of innovative projects, and so we use lots of IoT, Internet of Things, to collect data all along the value chain. So, for example, we connect data from truck and container during the transportation. We collect data of their positions, but we also have other sensors for monitoring other relevant parameters. We have devices embedded on industrial systems, and this happens both during the shipment from the supplier plant to the production plant, so the inbound logistics, and also within the plant itself, so during the production operations. So for this reason, we have a high number of third parties that are involved in this process. For example, we have both internal logistics operators, external logistics providers, and hardware providers. The involvement of so many different actors brings to an increase of the potential risks on the collection and the management of this data. For example, it can be easier to assess the data for tampering, in particular in the case where we use the devices on the inbound logistics, so they are external to our premises and we cannot have a direct control of what happens outside our premises. Or for example, the exact location is not always known, again, when the devices are not are external to the company. Um, Moreover, there is a high number of heterogeneous devices and a high number of actors that have access to all this data. And the impact of an event can be very high on the manufacturing processes because, for example, a delay in the supply or the assembly can cause production stops and, of course, additional costs to recover. And also there can be safety issues for the operators in case we are talking, for example, about robots. So for this reason, in C4IoT, we have considered two different scenarios. As also my colleague already mentioned before, we have a logistics 4.0 scenario and a smart factory scenario. So in the logistics 4.0 scenario, we have focused on the sourcing of components. As I already mentioned, in the transport from a supplier plant to a production plant, that is what we call inbound logistics. And in the smart factory scenario, we have focused on data that comes from AGVs, so automated guided vehicles, and robots that we use in plant operations, like in the assembly, in the welding, and in the material handling. Here you can see the business cases that we have considered. So we have 4 different areas, so the monitoring, the analysis, the mitigation, and the access. So for the monitoring, we have these 2 functionalities, so the possibility to monitor in real time the security level, the visual representation of the processes. Then we have an analysis aspect, so the analysis of the accesses to the devices, the analysis of the impact of the event. Then we have the mitigation, so there is the possibility, thanks to C4IoT, to define mitigation strategies to interact with the user for implementing the mitigation strategies and also to enact them. And then we have also the possibility to have access to the platform with some user according to the actor that needs to access the information. So which is the business value for CRF? We have the possibility to have a platform that allows to monitor the processes. We have the possibility to have this both from the supplier plant, but until the production plant. So both during the transportation, but even inside the plant itself. Since thanks to the C4IoT solution, we can monitor the Internet of Things installed both in internal processes but also in the inbound logistics. We have the possibility to have an analysis of the threats, to have a visual representation of the data and of all that is happening within the process, so we can have an immediate feedback of the status of the processes, and we also have the possibility to implement some recovery actions in case a risk verifies. So here you can see a representation of a container with the sensor and then the loading of containers in the truck, and here some sensors on a robot. Okay, so if we go a bit more in details of the data that we have in both scenarios. Let's start from the Logistic 4.0 scenario. Here we have focused on the shipment of battery packs. We together with our supply chain management have decided to select this component because it is a component that is more subject to the impact of some events, for example, in particular regarding the temperature, because as you know, batteries need to stay within certain temperature range, and it is something that normally doesn't happen during the transportation itself, when the batteries are within the truck. And so thanks to the implementation, to the installation of the devices that have been developed within the project, we have the possibility to track this data. But of course, not only the temperature, but we can also get data about the localization with the GPS tracker, and also vibration. That is also a relevant parameter in order to understand if the container has been subjected, for example, to shocks or changes of orientation, and this can have impact also in the quality of the transported components. So here you can see an example of some data that we can collect and retrieve thanks to the devices that we have installed. Moreover, here you can see also a representation of the localization data. For example, in the platform, we can have um, the information of the position of the container in a precise moment. So in each moment we can have the information of where the container is located. Sorry. And also we can have the possibility, thanks to the collection of all the data during the transport, so from the beginning, so from the moment of starting until arriving in the production plant, we can reconstruct, thanks to the GPS data, all the path that has been followed by the container during the shipment. So, just to add that in the next presentation, my colleague Giorgio Stamatis will better show how the end user visualize all this data on the C4IoT platform. So, the second scenario is the smart factory scenario, as already mentioned. This scenario has been developed in the Stellantis campus Melfi. So I don't know, maybe some of you have already heard about this campus. It is part of the Stellantis company, and it is an innovative center that is located in the Basilicata region in the south of Italy. The main important aspect is that it is an hub where small and medium enterprises of the region can have access, maybe in case we organize some visits or workshops. Here we have a reproduction of real plant lines, and also we test all the new products, innovative products that we test in the various projects, or also in our internal activities. So the small and medium enterprises there can have the possibility to assess the campus and see these new products that we test, and understand the benefit, for example, of IoT applied to robots, and understand which are the benefits of using these new technologies that we have there. In particular, in the scenario, we have focused on data coming from sensors installed both on AGVs, but also robots, where we collect similar data. In particular, we collect data about acceleration and the speed. You can see here the installation of one of the sensors on an AGV. And in the project, we provided from one side some historical data that have been used in order to develop machine learning algorithms to be implemented in order to identify anomalies in the data. But we also have near real-time data, and this allows to have a continuous monitoring of the status of the system, thanks to the usage of the developed algorithms. So here you can see an example of the data that we collect. In particular, these are velocity data of one AGV. Here you can see an easy representation of the architecture that we have developed in Melfi. So just to understand which is also the hardware that is involved, plus the cloud that is also included here. So what we had before the project were the AGVs and the robots that you see here at edge level, and a repository containing a database where all the data are stored. So in the project, we added our other components, so the field gateway PC that exchanges data to the cloud, that are in CRF premises, but also other components like the Sdn network and the Raspberry Pis at the edge level. Um, in order to use the C4IoT architecture tools. So all these components you see here, so both the Raspberry, the field gateway PC, the cloud, and the SDN network are all equipped with C4IoT tools, and in this way we allow all the data flow, the data analysis, the mitigation of threats, and all the functionalities that we discussed today. So, as already mentioned, the project is coming to an end, and at the moment we are finishing the evaluation phase. We don't have the exact values at the moment, but we expect to have the KPIs in line with what we planned at the beginning of the project. In particular, in this evaluation, we are considering some KPIs like the one I'm showing now. So the cybersecurity incident investigations that are resolved within an organizationally defined time frame, that will be calculated as a percentage. Same for the resilience of industrial infrastructure. And then we are also evaluating the cost effectiveness, the increase in productivity, in market share, and in sales. So, to conclude, in a nutshell, for CRF, we can say that we have gained some very useful functionalities that are the monitoring of both the inbound logistics, but also of the production process. We have the possibility to have a real-time analysis of the threats, and also an evaluation of their potential impact. We have the possibility to define and enact recovery actions. So these functionalities, together with some enablers like the dedicated hardware and the manufacturing, the embedded strategies for the threat identification, management, and recovery, bring us to have some benefits that are very relevant for us. For example, in the production, we can have an increase of the stock out, and improvement of the job per hour, and of the overall equipment efficiency. We have the possibility to decrease the cost for operations like the express delivery in case of delays, the warehousing, and the stock out. And also we can avoid the safety issues, and also avoid the loss of intellectual property. So that's all from my side. Thank you. And again, if you have questions, here you find website and Twitter page of the project. And also you have both mine and my colleagues Gianmarco Genchi email address, and so if there are any questions you can also contact us there.
Thank you, Elenia. I'm Yorgos Stamatis from ITML, and we will build up upon what has been presented so far. So you can see my screen, right?
Yes, we can.
Thank you, Elenia. So we're going to see how C4IIoT helps secure the infrastructure of the industrial environment, how the monitoring that was presented earlier takes place, and how the data that are produced by the edge are monitored, evaluated, and how the integrity is protected. And we're also going to see how specific threats are detected and how they can be mitigated through the C4IIoT framework. So we're going to start with a bit of the architecture, the hardware architecture. As it was mentioned already, we have the edge layer, the field gateway layer, and the cloud layer. On the edge layer of the logistics use case, we have the logistics devices that were presented earlier by both presenters. And on the edge of the smart factory, we have the Raspberry Pis. Now, the logistics devices, of course, are mobile devices, so they communicate using a mobile network with a field gateway layer of the mobile operator, who is A1 Serbia in our case. And the Raspberry Pis with the smart factory field gateway are, of course, both within the factory, so they are in the same network. Now, these two field gateways, through a secure connection, are connected to our main cloud server, but there are also two additional servers. One that has some additional components, we will see those in the next slide, and another server which supports the SGX environment, about which we'll also speak more on the next slides. So software-wise, this slide is trying to depict both the levels and the layers. This is why many of the components are repeated, because while they belong to a specific level, they are deployed in multiple layers. So on the logistics edge device, we have BAC-C, which was mentioned by Serjan earlier. On the logistics field gateway, we have the decentralized access control module, Medici, data fusion bus, the traffic analysis module, and another different version of bugs. On the edge of the smart factory, we have the Raspberry Pis with a decentralized access control module again, and the version of bugs. On the field gateway, we have decentralized access control, Medici, data fusion bus, bugs, data fusion bus, bugs, Disco, the Sdn Controller, and the traffic analysis module. And on our main cloud server, we have Karmas, the Advanced Visualization Toolkit, the full version of Data Fusion Bus, BinSec, the Security Assurance Module, the Bugs cloud version for the Smart Factory, and the Decentralized Access Control. On the auxiliary server, we have our private Docker repository, the certificate authority, and some components of decentralized access control module. And on the SGX enabled server, as part of this demonstration, we have the version of bugs that is for the logistics use case, the cloud version of bugs for the logistics use case. So let's see some of this per layer. The logistics edge is a board that was specifically designed for this framework by the University of Novi Sad. The data are transmitted through A1 Serbia mobile network, which is secure by design network, to the field gateway of the logistics use case. And these logistics boards are equipped with Infineon's Optica Trust-M component, the hardware-enabled security. And as mentioned earlier by Serjan, we have a machine learning model running on these boards developed in C programming language. which takes the data about the GPS and the acceleration and evaluates them before sending them to the next layer. On the smart factory edge, as it was mentioned so far by both presenters, we have the data from the automated guided vehicles from within the factory. Now this data evaluated on Raspberry Pis, which are again equipped with Optica Trust-M, but Optica TPM2 by Infineon in this case, again. And a Python machine learning model BACS for the Smart Factory Edge is running on these Raspberry Pis. And a Docker image for the ARM architecture for this case, which is the architecture of Raspberry Pis, was provided by the University of Novi Sad, which is suitable for running on Raspberry Pis in order to run these Python models there. Now, for both the field gateways, both field gateways are secured. They are isolated from the internet, and they are connected through a secure IPsec tunnel to the cloud only. The logistics use case field gateway is a Linux machine, and Smart Factory One has Windows operating system. This is important because it shows that this framework can work on both types of operating systems, so it can be used in any case. And I would like also to mention here Medici, which was mentioned in the first presentation by Serjan, because it's an offloading mechanism that runs on both these field gateways. And it's important because maybe in case of an attack or a different problem, one of these layers might be overloaded because of an event. So Medici will then choose which, if the evaluation needs to happen again, on which layer it will happen. So it might send the data to a different layer which is working as expected at the time, and reduce the load for the specific already overloaded servers. But we will see its exact place later during the monitoring part. And this, of course, adds resilience to the system. Now, our cloud, we have almost all modules running on the cloud are secured behind the cloud infrastructure, which is based on micro-K8s, a lightweight Kubernetes installation. This was set up by HPE. And as we mentioned already, we have a different server which is SGX enabled and provides the trusted execution environment on a cloud layer. Now, some things that the user can see using this micro-K8s dashboard is the workload status of the cloud. This is some visual representation from this dashboard. You can see if everything is running, some pods are currently trying to be restarted or they have failed. And this is an important view because to the ICT who will be responsible of this infrastructure, with a quick view, they can see if everything is running off, if there are problems somewhere. They can also see this screen, which is a consolidated view of all the pods running in this Kubernetes installation. And here we have the total CPU usage by the pods and the memory usage. So spikes in these screens might indicate that something is not working correctly or even be an indication of an attack. So it's a way to monitoring the installation itself. Of course, this system has ways to recover by itself, but the user can get more information using this dashboard. Now, this is a screenshot from a specific pod, the Kafka deployment on the cloud to be more specific, where again the user can see useful information about this pod only, the CPU usage dedicated to this pod and the memory usage of it. and of course if it's running and when it was first deployed, when it was ready, when it was restarted, and other useful information. Now moving on, one of the most important aspects of the C4IoT framework is the identity management through a private certificate authority. Now, this was also deployed by HPE. This is a screenshot from the dashboard, the graphical user interface of this private certificate authority. And all the certificates that are used within this project are created or signed by this certificate authority. Now, through this dashboard, the user has the option to create new certificates or sign certificates that have been created in some other way. And they can also revoke certificates, which is important in case you think a certificate has been compromised. You can revoke it through this dashboard. This is a common certificate authority for all C4IoT modules. And as part of this identity management, each module has its own certificate, which is important because it allows this module only specific access to the parts where it needs to be able to access. We will see some of this later as well. Another component running on the cloud is the security assurance module developed by Sphinx Technologies. Now, this component has a list of the organization assets. So these have been loaded, analyzed. They include everything that is all software that is running on them, a complete list. And a most important aspect that on these assets, vulnerability analysis is possible through this module. An example is here where a specific CV has been reported for a specific component, and this allows the user to see the vulnerabilities and patch them if possible. A dynamic testing is also possible through this module, which might reveal other vulnerabilities. And also part of it is Everest and the event captors, which can monitor specific services within the system. And in case that one of those is not working as expected or vulnerability is detected, this will be reported through the security assurance module. This is again a screenshot from SAM, which shows the most vulnerable assets. It has various graphical representations about the vulnerabilities that have been detected and the assessments that have taken place on the system when they were when they happened, and extra information about this and the assets that were evaluated. Now, another component of C4IoT framework is the private Docker repository, which is implemented with Harbor. Now, most of our modules are Dockerized, are in Docker containers. So it's important to have this repository, so to use specific images every time and images that have been checked. So here you can load either custom images or images that you have pulled as is from Docker Hub. And a most important aspect of Harbor is that it performs vulnerability analysis of these images. So, for example, this is a screenshot from the analysis of the image from the Elasticsearch connector. On the first version, many vulnerabilities were found. Most of them, there were critical vulnerabilities found. After the first patching of this image, these vulnerabilities were reduced. And then we actually decided to use a different image which had zero vulnerabilities. And another important aspect is that you can set a severity threshold on Harbor, which means that you can decide that, for example, if an image has vulnerabilities higher of critical than critical, do not use this image at all, which will alert the user of the system that a new image has to be created or this image has to be patched and does not allow high vulnerability images to be used by the system. And this is a screenshot from the part that shows the vulnerabilities of a specific image. The vulnerabilities appear on the list here, and this list is pretty complete. You have the severity for each CV detected, which package this CV is about, the current version, and if there is a version that this vulnerability is fixed is also mentioned here. Moving on, this is a video about BinSec from the Advanced Visualization Toolkit, which is developed by AES. BinSec is developed by CEA and performs vulnerability analysis on binaries. Now, in this specific case, the vulnerability analysis is on the BAC, which is the binary of running on the edge of the logistics use case. The user can choose the method to use for this analysis, the version of BAC2C to analyze, and what input to be used, and the time allowed for this vulnerability analysis to run. Here we see a past vulnerability analysis, a historical one, and the result that it provides. These results can be used by the user of the system to see if there is something wrong with this specific binary, and if needed, patch it or replace it. Now, a very important module of the C4IIoT framework is the Decentralized Access Control module developed by IBM. It has two important aspects. One is the attribute-based encryption, which is used for both use cases, and the other are the blockchain technologies. For the use case of the logistics, we're using the blockchain database, which is a database with aspects of blockchain, such as the immutability. And for the smart factory, there is an actual Hyperledger Fabric implementation. This component is used on almost all layers. This is a representation of the data flow, but we will see more details later on the monitoring use case and how this is used exactly within the monitoring part of the system. Now we also have Data Fusion Bus developed by ITML, which is built on Kafka. We chose Kafka for this framework because it can support a very high throughput of data, which might be possible in a big data environment, such in IIoT, in such as an industrial Internet of Things environment. So it adds to the resilience of the system. And of course, we have multiple topics to support the various modules. Many modules of this framework use it. Now, the additional part to Kafka is the Data Fusion Bus Admin API, which is used, consumed by the Advanced Visualization Toolkit on this screen. The user from this screen can provide read and write access to specific certificates. So the users are identified by the certificates, the common name on this certificate, and they can also ban a specific user in case a certificate has been found compromised, and also provide some information about the current status of the brokers and the topics at each layer. We also, on the cloud layer only, we have the storage connector, which its main usage is to store the data produced by the other layers on the Elasticsearch, which is our main storage for this framework. But it is also using the decentralized access control module to check the integrity of the data in transit. We will see this flow a bit later. Now, actually. So we're moving on to the monitoring use case, for the logistics use case more specifically. The data produced from the edge devices, from the logistics devices, and there they evaluated by BACC. This is all BACS on all layers performs anomaly detection. So the result is always if these data are okay or if they are anomalous. Now these data are sent over the mobile network to the field gateway of the logistics program, where they are received by a program created in order to receive this data. Excuse me. Now what it does is to use the decentralized access control module in order to add the hash of the data to the blockchain element of this module, and is also using the attribute-based encryption to encrypt this data. Now, on the next part, another decision that is made by this program and depends on the confidence of the evaluation that happened on the edge is whether to send the data to Medici or to cloud. If the confidence of the edge is high, these data are sent to the cloud through Kafka. If the confidence is low, these data are sent to Medici. The Medici is the offloading mechanism we discussed earlier. And now Medici, depending on the data it gathers from the two other layers, from the field gate where it's also deployed, and from the cloud, it will decide whether the re-evaluation of this data is going to happen on the field gateway layer or on the cloud layer by the BACS modules running on these two layers. Once the re-evaluation is complete, or if it's not needed, these data are sent to the cloud, where they're consumed both by the storage connector and by the advanced visualization toolkit. Now, the storage connector, before saving this data on the storage, again using the decentralized access control system, will check the data, will compare the hash that is already stored on the blockchain elements that was stored here against the hash of the data that have been received here. If these hashes do not match, that means that the data in transit somewhere within the system have been tampered with, so it will store them on a different index on Elasticsearch to be analyzed layer. If this hash is checked, it stores them on Elasticsearch and also adds the primary key that is assigned to this specific data point from Elasticsearch on the blockchain element. So now we have a complete entry about this specific data point on the blockchain element, which includes a unique data ID for this specific data point, a combination of the device ID that created this data and a timestamp, the hash of this data as close as to the edge as possible, and the primary key in the storage. Now, the AVT also consumes this data live from Kafka and displays them to the user. In order to do that, of course, it has again to use a decentralized access control system in order to decrypt the data, because the data in transit are always encrypted through decentralized access control. And the user can also use this system again to check the hash of the data that are displayed on the Advanced Visualization Toolkit against the one that is stored on the Decentralized Access Control module. Now we're going to see a video from the logistics monitoring on the Advanced Visualization Toolkit. This is the user interface of the system. The user can choose to see either the events or the monitoring part. Here on the event screen, all the data received by the old devices are depicted here. They're displayed here. This is a list of all the latest events received. You can see if the status is okay or if it's an anomaly. And this graph shows where the last evaluation of happened, if it happened on the edge, on the field gateway, or on the cloud, and also if the ratio the ratio of the anomalous versus OK events. Now, on this part of on this specific screen, again, this ratio is depicted and the last entry is received. But here the user can also choose a specific device to see information about this device only and the actual data. So these are the logistic devices that are currently deployed. The user chooses a specific device and clicks inspect device. And here the latest data received and some data from the Elasticsearch from the storage are displayed to the user. This data, as we mentioned earlier, okay, if there was an anomaly detected, it would be displayed here. This data, of course, are first decrypted and then displayed to the user here. And since we're talking about GPS data, as Elenia showed earlier, these are depicted on the map here as well. And also we have information about the acceleration, which in this case, each data point was taken while the device was stationary. Now, moving on to the historical analysis that is also possible through the Advanced Visualization Toolkit. The user again here has two options. One is to see a specific event. So they will have to choose the use case, the specific device, and a specific time and day. And they can see here, they will see on the map where this specific data point was taken. It's a map representation. And again, as we mentioned earlier here, the user can also validate the integrity of this data by clicking this specific button where the hash of the data is checked against the one stored on blockchain element of decentralized access control. Now, this is the time analysis of the timeline analysis of the logistics use case of the historical data here, where again a specific device has to be selected and daytime. And here we have this shows where its event was received during the day, if where the detection took place, on which layer for each of the data point, and if it was okay or anomalous events, if they were okay or anomalies. And of course, the data can again be verified using the hashes and decentralized access control. And the user has also the option to download the data. Here an aspect of the identity management mentioned earlier through certificates is used. So while the user can see the data, as we saw earlier, that does not mean that he or she also owns the data. So in order to be able to download the data, they would have to provide the personal certificates. These certificates, as you saw, they are provided through this graphical user interface, are used to get new keys from the attribute-based encryption part of decentralized access control, and then use these keys to decrypt the data before download them. This is why this is taking some time, because lots of data have to be decrypted and downloaded again. If the user does not have the appropriate certificates here, they cannot use this to actually download the data. So this is part of securing the data. Now you can see that we're going to save the data in CSV form, and you will actually see the data. So again, we have the ID that produced this data, if it was an okay evaluation or if it was an anomaly, the timestamp, the acceleration values, the GPS values, and other values sent by the logistics edge devices. Now, moving on to the monitoring of the smart factory, the flow here is very similar to the one we saw for the logistics use case, but in this case, our edge are the automated guided vehicles presented earlier, which produce data about acceleration and the velocity of two motors on them. These data are evaluated by bugs on the Raspberry Pis of the edge. In this case, we have a component, a part of decentralized access control on this Raspberry Pis as well. So in this case, the hash of the data and the encryption of the data actually takes place on the edge. Now, the edge here will have to take the same decision as the logistics edge, which means if the confidence of the edge is low, they will have to send the data to Medici. If it's high, they will send them to the cloud through the field gateway, of course. If the confidence is low, again, Medici will have to decide whether to send the data for re-evaluation on the bugs running on the field gateway, on the bugs running on the cloud. This takes place through Kafka. The data are sent through Kafka. And in any case, both these components, if they have to re-evaluate the data, they will also have to decrypt them using the decentralized access control module. And again, this data are received both by the storage connector and the AVT, and they perform the same checks and allow the same uses that also we already presented in the logistics use case. So these are some screens from the previous prototypes of about the smart factory use case from the advanced visualization toolkit. So this graph shows if the number of evaluations taking place on the edge, and if we had also evaluations on the cloud and on the field gateway, we would have the ratio here, the ratio of anomalous versus OK events. These are all the events received at the time they received and the evaluation, if they are anomalous or not. And if a specific event is clicked, you will see more detailed information here about which device it was. Again, of course, if it was an anomaly or not. The confidence at the place that this evaluation took place. And when choosing a specific device, you can see more information about this device. Again, of course, a ratio of anomalous versus OK events, the last received event about this device, and here the actual data. So here the data again are decrypted before shown to the user, and the graphical representation of the acceleration of or the velocity of the motors depending on what the user is going to choose. And the historical analysis, multiple data from the past can be they are displayed here in a graphical in this figure, where both the acceleration of both motors is displayed in one single graph, so it can be used for analysis by someone who knows the system better. Now, I would like to mention a few things about the traffic analysis module, which is developed by Forth. This module can, using signature-based technology, can make specific detections about specific attacks. So it can detect some types of malware. It can detect some types of man-in-the-middle attack and session hijacking, brute force attack, and network scan. So this module monitors the network data in order to be able to produce and detect these specific attacks. And I would also like to mention the DISCO, the Sdn Controller, which is developed by Thalys. Now, this is attached to the software-defined network in the smart factory, and it has the capabilities to isolate an IP or a MAC address by dropping all packages that are directed to these addresses, or it can filter a specific port of a specific IP to block any communication towards that port. And it also can limit the flow towards a specific um, IP again, in order to limit the potential of an attack. Now we're going to see how these are used from the system. We are assuming an attacker. Now this could be an external attacker or some other compromised system within the factory, for example. Uh, so it's trying to attack another asset through the network. This attack is detected by the traffic analysis module and is reported through Kafka to the cloud. Now, from the cloud, this attack is consumed both by the Advanced Visualization Toolkit and from SAM. The Advanced Visualization Toolkit displays an early warning about this attack, and SAM takes the Security Assurance module, takes this information, adds additional information about it, and also sends it to Advanced Visualization Toolkit. Now, the user here is going to, when see the attack, and request mitigation actions from Karmas. Karmas is a module deployed on the cloud, and it receives, it's exposing an API which can receive information about an attack, such as the IP and the severity, the plausibility of this attack, and return information about mitigation plans, a specific mitigation plan for this attack. So when this attack is this mitigation plan is requested by the AVT, it can then be applied using the Sdn Controller. So in this case, the attack would be blocked. Now we're going to see a demonstration of this from our test servers. What we're going to do here is create an attack with this command. This command will start a brute force attack between two containers. One is the attacker and the other is the one under attack, simulating, in this case, assets of the factory. So when this command will start running, we expect to see here reports. I didn't start there, I'm sorry. We expect to see here the attacks reported by the traffic analysis module. Now this attack takes some time to start. It takes as input two files. One is a list of possible usernames, and the other is a list of possible passwords. So it's a dictionary attack actually. And this will start attempting combinations of these two lists until it finds the actual credential. This is an attempt to find the SSH credential of the second asset. So the attack has now started. What we expect to see here is the attack reported by the traffic analysis module. As you can see, it has already started reporting anomalies. By clicking on one of these, you can see a few more details about it. You can also see that a threat flashing button has appeared here, that is to notify the user about a possible attack. The more details here is that this attack was detected from the factory traffic analysis module, and that, of course, it was an anomaly in the time that it was detected. Now the user can click the threat detection button or go directly to the attack monitoring screen. In this case, the button is used. Now, this is the attack monitoring screen of the Advanced Visualization Toolkit, where the user can see more information about this attack. Now, the source IP of the attack, the destination IP, and the type of the attack were reported by the traffic analysis module, but the rest of the information were added by the security assurance module. So about the operating system, in this case we have impact and risk, but these have been replaced in later prototypes. Let me remind you that the security assurance module has a list of the assets, so it's in position to add the extra information about this. And it also has more information about the specific attack, which is to do so more, to be more informative to the user of the system. And also below there is a list of the attack history. Now we have a list of this specific attack because it's a continuous attack. In any case, any of these events can be chosen and see the exact information about this. In later prototypes, these have been grouped in a different system. And as I mentioned already, impact and risk have been replaced by a single value. Now the user here can choose to either ignore the threat or request mitigation plans. If the request mitigation plan button is clicked, as I mentioned earlier, a request will be sent to Karmas, and Karmas will respond with the most appropriate mitigation action for this attack. So in this case, the suggested mitigation action is host isolation. When the user clicks on this button, this mitigation action is going to to be applied through the Sdn controller, and what we expect to happen is the attack that was running so far to stop. As you can see, this has already happened here. The attack that was continuously running has now stopped because this asset no longer has access to the asset that was trying to attack since its IP had been isolated. So what we're going to do is manually stop the attack and try to restart it just to verify that this asset is actually, its IP is actually blocked. Move the video forward. So we're going to manually stop this attack and try to restart it. But in this case, the attack will not start at all because this IP is no longer reachable. So the flow that you see here in our latest version can also be automated. We have added a automatic mitigation. This is the screen from the Advanced Visualization Toolkit where the user can set up a specific rule. So, of course, a name for the rule in order to assist the user in to identify what the specific rule is about, a specific address, a specific IP address, and what type of attack should take what type of specific, mitigation action. And on the side, there is a list of the mitigation rules that have been that are already active, and these can also be deactivated in order if there is no longer use for them. So in this case, the flow would be similar to what we saw before. The attacker is trying to perform an attack to another asset. This attack is detected by the traffic analysis module and reported to the cloud. But in this case, the attack is received by the storage connector. We're using this module because it's a module that is running continuously in order to store the data. So it's ideal to receive all the attacks. So since it's running continuously, as I mentioned earlier, in which case the connector will check on the storage if a specific rule for this attack that was received now exists. We're talking about the rules that were added through the Advanced Visualization Toolkit that we saw in the previous slide. And if a specific rule exists for this specific attack, it will try to apply the mitigation action through DISCO, the Sdn controller, in order to stop the threat automatically. This concludes this presentation. Thank you very much. And if you have any questions, please feel free to use the chat or contact me directly. Thank you.
Thanks a lot, Georgos, for your presentation. So I see there are no questions in the chat, but okay, again, if you have any questions or you would like to have more details, feel free to contact us directly via email. So thanks again to all of you for participating and so we can close here since we have talked about all the planned points. So thank you again and have a nice day. I hope to be in contact with you in the future again. Bye bye.